Hello friends, welcome to a lecture on WXMaxima. Now this lecture has been specially made keeping chemical engineering professionals, chemical engineering teachers and students in mind. Here I wish to demonstrate the power of WXMaxima, that is a computer algebra software. Would you believe that there is a software which can give you analytical solutions for the problems that you have posed? Would you also believe that there is a software where you can get answers to tough problems, very complicated ones, without resorting to programming? WXMaxima is a computer algebra system. Rather than taking mathematical problems and demonstrating its full scale and scope, I will take problems in engineering and demonstrate the utility of this software. Computer algebra systems are fantastic. They are a fantastic learning tool. They are a fantastic demonstrating and research tool. One should know, and in his entire career, if you're in STEM, that is science, technology, engineering, or management, one should learn this software, that is to use any computer algebra system. Well, you have Mathematica and Maple, which are computer algebra systems, but they are very expensive. WXMaxima is free to download, and therefore it's fun to use. Free to download does not mean that it's not effective, it's badly written, its results are inaccurate. It's the exact opposite. It's a well written software, results are fairly accurate, and the user interface is simply superb. Let's see the demonstration. Let's take a problem in chemical reaction Equilibria. What we have is a water gas shift reaction where carbon monoxide and steam makes carbon dioxide and water. It's performed in a reactor. The equilibrium constant for the reaction is given by the expression K equilibrium is equal to exponential 4577.8 divided by the temperature, which is in Kelvin, minus 4.33. Now the reference for this expression is JMO Chemical Engineering Progress, volume 58, published in the year 1962, particular page 33. We take a problem here. 1 mole of steam enters for every mole of carbon monoxide. Let's find the value of epsilon for a temperature of 1100, 1200 and 1300 Kelvin. Now, as we can see, the reaction will be unaffected by pressure as the volume does not change. That is, the total molarity of the reaction does not change. Also an information that the reaction is exothermic at standard state. Now, if epsilon is the extent of a reaction, pardon my English once again, extent, E-X-T-E-N-T, extent of reaction, then the moles of carbon dioxide, hydrogen, carbon monoxide, hydrogen, carbon dioxide and uh, carbon monoxide, steam, carbon dioxide and hydrogen at equilibrium are 1 minus epsilon, 1 minus epsilon, epsilon and epsilon. Well, if this is 1 mole and the extent of reaction is epsilon, so the moles at the end of the reaction is going to be 1 minus the stoichiometric coefficient, which would be minus 1 into the epsilon. So we have 1 minus epsilon for carbon monoxide and epsilon for carbon dioxide, and the similar logic follows for others. The total moles at equilibrium are 2. If we add all these, the answer is 2. The mole fractions for each and every component are now 1 minus epsilon over 2, 1 minus epsilon over 2, that is for carbon monoxide and steam, and for carbon dioxide and hydrogen it is epsilon by 2 and epsilon by 2. The expression for K, or the expression for the equilibrium, I will write it in terms of x. I won't write it in terms of epsilon because x is easier to type on the keyboard and epsilon is something I will have to select each time. So let me write the expression. So the equilibrium expression is going to be 1 minus x divided by 2. That's it. So that's 1 minus x multiplied by and this entire expression on the numerator is we are going to have x by 2 star x by 2. So this is the expression that we are going to have. I can add as many parentheses I require to make things more clear. So it is x by 2 into x by 2 on the numerator and 1 minus x by 2, 1 minus x by 2 on the denominator. And whenever you want to add an expression or whenever you want to execute a command, you have to press shift and enter. Now this particular command assigns this expression to this name, that is equal expression. So if I write EQUILEXPRN and press shift and enter, I get back the expression. So it's a short for the expression. Now we have an expression for k, and k can be written down as a function. So whenever we want to write down a function, we write it this way: kt, where k or equilibrium constant is a function of temperature, is equal to, so we put colon and then put equal to and write the expression. So the expression is, let's have a look. The expression here is exponential. So we write percentage e for the exponential. This is going to be 4577. That's 4577.8 divided by the temperature. Now we write the expression for solving the problem. Now the LHS of the equation will be the equilibrium constant and the RHS of the equation will be the expression in terms of moles, that is this expression. So therefore we make a new expression, write a new expression for this. So we write K and we solve K for 1100 and we write the expression. So we get back the expression now. So now this is the expression first, and this first expression is for a k value of 1100. Now we have to solve this expression. So we write solve and there we go. It's solved. It gave me an analytical solution for the expression. Now if I want a numerical solution for it, all I have to do is write float and include this command in float, and there we are, 0.4789. That is the value of x. It's evident that the conversion is 47.89. Now, how do we use it? Now let's save it. Now I want to do the calculation for 1200 Kelvin. So all I do is go here, instead of 1100, I put 1200 here, come back to this point, go to cells and go to evaluate cells below. And as you can see, it has re-evaluated the cells below after the expression, and we have got the value of the conversion, which is 43.5. Now let's solve this for 1300, and there we are done. 0.400. So as we can see, from 48% we have come to 40%. The conversion has decreased. And this is not surprising because the reaction is exothermic, and as per Le Chatelier's principle, if we increase the temperature, the equilibrium should shift towards the reactants. Now, as you can see here, this is a very excellent tool to solve problems. It solves the problems by itself without any programming. Therefore, this is a must-learn software. One should invest time in learning it. It could solve far more complicated problems. I will be taking a series of lecture on this, taking up a few complicated problems from transport phenomena and subjects where I feel the problems are quite complex, and demonstrate that how this software actually helps us in solving it. Why I am not taking pure mathematics problems? The reason is I want to cover up a series of lectures which demonstrate that how this tool is powerful enough to solve engineering problems too. That will be all, guys. Have a great day. Goodbye.